Hi, this is Dr. Ricker, and this lecture for Psychology 200 is from Chapter 2, and it's on research methods. Okay. Psychology has three main goals. At the simplest level, we want to describe something, usually behavior, but sometimes we might describe how somebody's thinking, or we might describe what's going on in the brain, but we're just describing something. We're not really saying anything more than that. Sometimes we want to do a little more than that. Sometimes we want to predict. So we might observe a behavior in somebody and predict that in the future we'll observe a different behavior based on what we've observed. So we're doing a little bit more than just describing it. We're actually predicting something else. And then at the deepest level, we would really like to provide an explanation. Why did that person do what they did? We can't always do that, but we would like to do that whenever we can. I'm not going to say too much about description in this particular video. You can read about it in the textbook, and the next video that I have from Chapter 2 on statistics talks a little bit about how we use statistics to describe something. So I'm going to start talking about prediction. And when we talk about prediction, we use something called correlation usually. For correlation, you measure two variables, you measure two different things, so it might be two different behaviors or two different tests, or a test and a behavior or whatever. You measure two different things, and you look to see if those two things are related to each other. And usually you will put them out on a scatter plot to get an idea of what your data looks like. So these are three different examples of scatter plots. One of the variables will be plotted along the x-axis, and one will be plotted along the y-axis. In just a second, I'm going to show you some examples with some actual data, and I think it might make more sense to you then. And each dot here is one of your observations. Often it's one person, but it's not always a person. It might be something else. So it's one of your observations. And if the dots tend to follow along a line that slopes upward, that tells you that there is a positive correlation. Just as important, if the dots follow along a line that slopes downward, that tells you there is a negative correlation. If the dots are all over the place, like this one over here, that tells you there is no correlation. The two variables are not related to each other. So now I think this will make more sense if I show you some actual examples. Here's an example of a positive correlation. This is the correlation between a student's high school grade point average, plotted here, and their SAT score plotted here on the horizontal axis. So again, each dot is a person. This person here had a really high GPA, almost 4.0, and they scored really high on the SAT. These people down here had lower GPAs, and they scored lower on the SAT. So you can see that these dots tend to follow along a line. The line is just the best fitting line that kind of fits within those dots. They follow along a line that slopes upward, which tells you there's a positive correlation. People with a higher high school GPA tended to score higher on the SAT. That means we could use one of these variables to predict the other one. If we know somebody's grade point average, we can predict what SAT score they will get. It's not going to be a perfect prediction. Sometimes people score a little higher than expected or a little lower than expected, but we can make an educated guess as to what SAT score they will get. Just as important is a negative correlation. It's often a little more difficult to think about a negative correlation, I think, but they are just as important and just as informative as a positive correlation. Here's an example of a negative correlation, the correlation between the price of peaches and the number of peaches sold. And it doesn't matter which is on the x-axis and which is on the y-axis. We could just as easily have switched them. Again, each dot is a data point. So here, these were peaches that were very expensive, and as you can see, not very many of them were sold. Over here, we have the cheaper peaches. They're down here on the vertical axis, and you can see more of them were sold. So this is a negative correlation. As the price of peaches goes down, more of them are sold. You see how the dots follow along a line that slopes downwards. So if you know the price of peaches, you can predict how many will be sold. If it's a low price, you'll sell a lot. If it's a high price, you won't sell as many. So this allows you to predict. Either a positive or negative correlation allows you to predict. When you cannot predict is when you have zero correlation. That means the two variables are not related to each other. The dots are just falling all over the place like this. This correlation is between what is that? Oh, the number of, this is looking at television shows. This is the number of people who watch a particular show on television And this is the number of people who downloaded it on the internet. You might think there would be a relationship between those two, but as you can see, there's not. Knowing how many people watch the show on television does not allow you to predict how many people will download it from the internet. Those are two independent things. They are not related to each other. The very important thing to remember about correlation is that correlation does not imply causation. And you hear people say that a lot, but I really can't emphasize that enough. If you have a correlation, you can say that your two variables are related to each other, but you cannot say what caused that relationship. So if you have two variables, say A and B, and they're related to each other, it may be that A caused B. It's just as likely that B caused A, or there could be some other variable, C, that is affecting both of them together. You don't know just by the fact that there is a correlation. You might try to guess, you might try to design some studies to determine what it is, but you cannot infer causation just based on the correlation. So to emphasize that, I want to show you some actual correlations that exist and have you think about possible explanations for why those correlations exist. What could have caused them? Because there's always more than one possible explanation. There's not going to be just one. So I'm going to put this up and then I'm going to give you a minute or so to think about it. And I'd like you to think about it, maybe even write down your answers, because if I will eventually give you some possible answers. There's no right or wrong answers here. There's just plausible answers and less plausible answers. And I'm going to give you some possible plausible answers eventually. But you'll actually understand this better if you try to figure it out on your own first. So I am going to pause for a minute. And you might even want to, in fact, I would suggest that you click on pause on the video and think about it and write down some answers before I go on. So the first one is there is a negative correlation between the number of hours somebody spends online and their social skills. So the negative correlation means that people who spend more time online have worse social skills. And I'd just like you to think for a minute about why that might be. What might cause that? And I would recommend that you pause the video here and think about it, maybe write down, try to think of at least two possible explanations. So there are many possible explanations. One obvious one might be that spending time online weakens somebody's social skills. When somebody's spending a lot of time online, they're not talking to people in the real world, and therefore their social skills suffer. They don't develop their social skills. So in that case, the hours spent online are having an effect on the social skills. It's just as plausible that it could be the opposite. It may be that somebody's social skills affects their hours online. Maybe people who have really poor social skills don't like talking to people, so they spend more time on their computer. So in that case, it's the social skills that are causing the hours spent online. Both of those are equally plausible. It's also very plausible there could be some other third variable that hasn't been mentioned here that is affecting both of those. Here's another example I'd like you to think about. There is a positive correlation between height and memory amongst elementary school children. So that means that taller elementary school children have a better memory than shorter elementary school children. And keep in mind, elementary school children means a wide range of children from kindergarten up through the 6th grade. So now I'd just like you to think about this for a couple minutes and think about one or more plausible explanations for why that might be. And I would recommend you pause the video while you think and try to come up with one or two good explanations before I give what I think is a good explanation. Now in this case, you might say, well, maybe being tall makes you have a good memory. Taller people have better memories, so somebody's height causes them to have a better memory. Or, but that doesn't sound very plausible, does it? Or it might be that having a good memory makes you taller. Somehow if you have a better memory, you remember to eat your vegetables, and that makes you go taller. That really doesn't sound very plausible either. A much more plausible explanation is that there is a third variable, and that third variable would be age. Amongst elementary school children, they can range in age from 5 to 11. And of course, as they get older, they're going to be taller. They will also probably have better memories because as kids get older, they tend to do better on a lot of different types of tests, such as memory tests. So the older kids are both taller and have better memories. So it's not that height affects memory or memory affects height. There's some third variable, their age, that is affecting both of them and causing the positive correlation. And one final one, there is a positive correlation between the number of hours a child spends playing video games and aggressive behavior. So I'd like you to think about 2 or 3 possible explanations for that and pause the video and think about it. This is a very good example because this is a correlation that has been cited by many people, and many people want to say that playing video games causes kids to be more aggressive. So there is a relationship there, and it may well be that playing video games does cause kids to be aggressive. That is possible, but it's not the only possible explanation. It could be that kids who are aggressive for some other reason enjoy playing video games. So therefore they're aggressive first, and then they choose to play more video games. So it's the aggressiveness that is causing them to play the video games. It's also possible there's some other variable that is affecting both of them. For example, maybe the parental oversight. If their parents are never home, they're free to do whatever they want, and they might spend all their time playing video games. They might also develop aggressive behavior because nobody's ever disciplining them. So it's the parental oversight that is causing this positive correlation, a third variable that wasn't measured here. So I just wanted to illustrate to you that anytime you see any correlation, there are multiple possible explanations, and you cannot just jump to the conclusion that one thing is causing the other. But now I want to go on and talk about experiments. In an experiment, if you have a very well-designed and well-controlled experiment, you can start to draw some inferences about what is causing a behavior. So in an experiment, the researcher doesn't just measure 2 or more things. They actually manipulate one of the variables. These are some examples. Experiments are almost always done in the lab. In an experiment, the researcher wants to have a lot of control over their subjects, so it's usually done in a lab. Here's a picture of B.F. Skinner working with a rat in a Skinner box. The rat is in this box. There's nothing there except this lever for it to press, so Skinner has very good control over that rat's environment. Here's a picture of a human doing a test on a computer. There's stuff on the computer. She's pressing a button. It looks like there's an electrode there measuring something. These are just 2 examples. There are many different types of experiments. But the main idea is that in an experiment, the researcher assigns subjects or manipulates the independent variable. They don't just measure what they get. They actually manipulate something. So you need to know the difference between the independent variable and the dependent variable. And this is something that a lot of students have a lot of trouble with. The independent variable, abbreviated IV, is what the researcher manipulates. So that is what the researcher is manipulating. The dependent variable, or DV, is what the researcher is measuring. Okay. So in an experiment, you are trying to determine whether the independent variable affects the dependent variable. So the independent variable, what the researcher manipulates, is what is going to have an effect on the dependent variable, not the other way around. And I think it can help to, whenever you read about an experiment, if you try to word it in terms of the effect of one thing on another thing. The thing that is doing the affecting is the independent variable, and the thing that is affected is the dependent variable. So try to word something in terms of the effect of something on something. Sometimes when you read a study, the actual title of the article is the effect of something on something. So then you know the first thing is the independent variable, and the second thing is the dependent variable. But they're not always worded that way. So I want to show you a few examples that are worded that way. Of some actual studies that could be done. If you want to do research on the effect of alcohol on reaction time, the alcohol would be the independent variable. You would want to manipulate that. The researcher would randomly assign half of the subjects to drink alcohol, and the other half would not drink alcohol. And then you would look at their reaction time, how fast they can react. The effect of a high-fat diet on cholesterol levels. So there, the diet is the independent variable. The researcher would randomly assign some people to eat a high-fat diet and others would eat a low-fat diet. And then the researcher would measure their cholesterol levels and see if there's a difference. Cholesterol levels would be the dependent variable. You could look at the effect of a drug on the number of headaches, or really the effect of drug on almost anything. The drug is the independent variable. You would randomly assign some people to take the drug and others would probably take a placebo. And then you would measure the number of headaches they get. That would be the dependent variable. Now, these examples are not always worded in an easy manner like that. Sometimes it's a little less obvious. So I'm going to give you a less obvious example and see if you can figure it out. So Dr. Rickert, that's me, seeks to determine whether students learn more in her class when she takes attendance. So she regularly takes attendance in her morning class and does not take it in her evening class. At the end of the semester, she compares the grades of the two classes. So why don't you pause the video right now and try to figure out what are the independent and dependent variables. Don't answer the last question yet. I haven't talked about that yet. But just pause the video and try to think of what is the independent variable in this case and what is the dependent variable. Okay, in this case, Dr. Rickert is trying to look at the effect of taking attendance on grades. So the independent variable is taking attendance, and the dependent variable is grades. She wonders whether students in the class where she takes attendance might get better grades than those in the other class. So the independent variable is taking attendance, the dependent is grades. Now, what I haven't mentioned yet is possible confounding variables. This is actually not a true experiment because Dr. Rickert did not randomly assign students to be in one class or the other. She just took the students in her morning class and compared them to the students in her evening class. So it's actually not a true experiment. And when you don't randomly assign subjects to the independent variable, you can have confounding variables. A confounding variable is a variable other than the independent variable that varies along with the independent variable, which might not sound like it makes much sense. But in this case, the independent variable was taking attendance. If there was any difference between the two classes other than taking attendance, that might be what caused the difference in the grades. If you have a confounding variable, you don't know whether your results are due to your independent variable or to the confounding variable. So you want to minimize confounding variables. And if you randomly assign your subjects to the two conditions, if I was able to randomly assign subjects to two different classes, that would minimize the differences between the two classes. So now try to think about what might be some possible confounding variables. What might be some differences between my daytime class and my evening class that might change the grades? And again, you can pause the video and think about your answers. So for this question, unlike the other two questions, there was a definite right and wrong answer for the other two questions. For this question, there aren't definite right and wrong answers. They're just more or less plausible answers. So a few plausible ones that I thought of are obviously time of day. You know, maybe people just learn better in the morning than in the evening. So I might find that my daytime class where I take attendance gets higher grades than my evening class where I didn't take attendance, not because of the attendance, but because of the time of day. So that would be a confounding variable. Any other difference between the two classes? It could be employment. Maybe the students in my evening class are working all day and that's why they're taking an evening class. And because they work all day, they don't have time to study, so they don't do as well because of their employment. It could be age. It may be that older students are more likely to take classes at night and younger students are more likely to take classes during the day. And if that makes a difference in their grades, that would be a confound. And then there's many other things it could potentially be. So that's just something that you need to watch out for. Okay. So that's it for my lecture on research methods. I also have another lecture for Chapter 2 on statistics, and you can also see that in the same place. I would encourage you to watch that now.